The critical point that we just identified that was neither a max nor a local min, they're most typically saddle points. There are other slightly more exotic types of critical points when we talk about surfaces, but the most common one seen in the wild is a saddle point. And what is a saddle point? Well, it has that property I mentioned in the previous pages, where this point is in some sense a local maximum when we're passing from one direction to the other, and a local minimum in a second direction. So it's somehow a flat point, well, or more importantly, it has a tangent plane that would be flat. That's an idea that comes from the gradient or both derivatives, both partial derivatives being zero at that point. But it's not a local maximum or a local min, which would be the other types of diagrams or other types of shapes, surfaces, that would have a tangent plane that's perfectly horizontal at the point that's the local max or local min. So all three of these are critical points: maxes, mins, and this saddle point. There's another important feature in terms of how we can identify these saddle points in contour diagrams. Saddle points occur at the crossing of two different contour lines. Why is that an interesting point? Well, remember that the gradient at a critical point is equal to the 0, 0 vector, or the 0 vector simply. And the idea being that it has no direction, no magnitude either, but for us with the properties of gradients, it's more important that we say no direction. The other property that we had about gradients is that the gradients are perpendicular to contours. So if you wanted to identify critical points, so critical points are points with zero gradient, they have to be points where we can't talk about a perpendicular to the contour. That's certainly not the case anywhere in this diagram. Here, we can talk about perpendicular. Pick any point on the plane, in fact, and I can talk about the line perpendicular to it. Doesn't matter where I go here, there we go, perpendicular. But at a crossing, ask yourself, what direction is perpendicular to all of the contours through that point? Well, I need to be perpendicular to this one, but I also need to be perpendicular to that one. I can't. I just can't draw something that's perpendicular at that crossing of two contours. When it's a simple curve, easy. And we know that we can generate a gradient that points uphill at all these other points. The point where our contours cross, where two contour lines intersect at the same height, there we can't talk about a perpendicular direction. And so we end up saying, well, the only possible way the gradient can be defined there is if there's no single direction, or if our gradient is the 0 vector. So there's a really nice tie-in between our understanding of the relationship between contours and gradients and the idea of critical points here. Another just general comment is the shape here is something that's new in terms of being a multivariate function. We couldn't have this kind of shape in a single variable function. We couldn't have this combination of a minimum in one direction and local max in the other because we only had one direction. So this is a new property or a new kind of object that we can only see when we have functions of more than one variable.